Ladies and gentlemen, welcome to a recording of the Chapter 7 review. Starting with number 11, that's really corny. I'm going to record normal. It is recording. So on number 11, since you asked for it, this is a little help to get you over that hurdle. The couple things you want to take into account, I'm going to record some things. There's an initial value, and there is this like population growth rate. If you hear the word relative growth rate of a population, you're probably going to be considering an exponential function of some kind. So I'm going to turn the page. Let's see if I can go over to the next page. Come on, over to the next page. There's the next page. If I pull up this function, here is population is equal to P naught e to the kt. That's a standard form of an exponential growth function, where P naught right here is your initial amount, back when you're a little peanut, back in the early days. And then there's this growth rate, little growth rate right there. And if you look back at our problem on the previous page, if I go back there real fast, we have a P naught, that's P of 0, 83,400, and we have a K, an initial kind of a growth rate, relative growth rate, 0.047. We're going to use those on the next page. So that's what we're doing. So if I go P is 83,400 e to the 0.047. I'm bad at remembering numbers when I flip the page. T. That's our function for population. Totally usable, ready to be banked upon. And it says write a differential equation for that. Oh, man, differential equation's even easier. If you want to work it out by hand, you're welcome to. But you should also know there's something super cool about these exponential growth functions. The derivative dp dt is just k times p. It's some multiple k times p. And hey, what do you know? There's k right there. So if you take a look at that, that's going to be our derivative, our initial value. So kp. It's actually a statement of the fact that exponential growth functions, the rate at which they grow is directly proportional to the actual function value itself. So this problem becomes relatively straightforward. If it asks you for, hey, what's the differential equation for this thing? It's that 0.047p. So I'm going to go red on this one. Come on, red. So, 0.047p. That's your dp, and I'd write dp dt in front of that if I had more room. And find the formula for the population, which is what I did on the previous page as well. Squeeze it in there, that 83,400 e to the 0.047t. That's 11. 12, you're looking for that. This one is, it's totally logistic. It tells you it's logistic. And there's like these little clues like p squared and p. The form we want, though, is we want something p times L minus p when we're looking at the differential equation. The k goes there, and the L goes here. If it's not in that form, it usually means there's some algebraic means to getting there. And so for us, we're going to factor out, since this is a singular p, that p right there, we're going to divide out the extra stuff. Like we're going to divide out the negative 0.000075p out of that so that we can get a singular p. It will leave behind our L value, and out front you're going to have your K, which if you can kind of imagine, it's going to be that 0.000075. So that becomes, if I can squeeze this in here, see if you can do the algebra on this one, 0.0000075. P gets factored out. And what's left inside times, since I'm running out of room, I'm going to go down to another level. Kind of following that. I'll write it on the other side too. L, which we'll get in a minute, minus P. Well, this little piece right here, the L, that comes from taking our 0.06p and dividing it by 0.0075p. So 0.06 that used to be there got a 0.000075p divided out of it. And the p's cancel. And so whatever our calculator gives us for 0.06, and I have to type it in, I forgot what it was, 800. So L ends up being 800. Thank you. So 800 goes in there. I'll put in orange. That's your L. So it's a pretty standard thing to see your differential equation in this form. It just means to factor out this coefficient that you see in front of the p squared, and a p gets factored out of both of those. That'll show you your k, and it'll show you your L. It'll get you both. And then the rest of the questions are awesome. Find k, got it, bingo. What's the initial population amount? Find a formula for the population, bingo, we just got it. How long will it take for the mountain lion population to reach 450? That's a means of just saying, hey, 450, oh no, can't do that, highlighter. 450, set that equal to our population formula, which was, I don't have my population formula. No, but I know what it is. On the next page, let's go 2 pages out, add a page. If you've got a k, remember a logistic? Oh yeah, you know what your logistic function is? Lice CE minus licked. That's the population function. If we're going to do any question about population, which this is, so if you look at this down here, it says, please tell me how long for the mountain lion population to reach 450? I got to go to the population function. This is the logistic population function. We've got an L of 8 hundo. 1 minus, I don't have a C. Not yet anyway. E to the negative 0.047 times my L of 800. T. Yeah. No! My assistants in the video production facility have told me it's a plus C. Thanks. Fixed. And then that's our function. We got to get C. So any ideas, assistants in the audience? How do I get my C?
You guess.
Yes.
Don't guess.
Lucky number 7.
No! You guys are no help at all. You put in your initial value, you nincompoops.
Nincompoops, that's disrespectful.
I'm talking to my studio audience, not my students. I would never, ever say that to my students.
Yeah.
Okay, so we got to put in 20, what was it, 25? Before we can answer this question, I got to go get C. So I know that's a little bit painful, but we can't do this without C. So you go 1 plus CE to the negative, oh no, 0.047 times 800 T. That point we solve for C. And then you can answer the question at the end. We'll get there. Hang tight. You guys can hit the road. I'll see you soon. Digitally sooner than later. You'll have a test mañana. And I don't have the C in front of me unless you guys want to spit the C at me. Does anyone know what it is by the chance?
Absolutely not. I'm sorry.
So getting back to where we were, this is doing that initial value to solve for C. There would be a 0 in for the T. Forgot to put the 0 in there, but I'll put that back in a little bit. But that's it. So we got to find C, and then we'll use then we'll get the whole function together. So here it is. I got 25 equals that. I'm going to swap sides with the 1 plus the denominator and that 25. We're going to swap. It's classic algebra for you. Hey, I forgot to put the 0 in for T again, but hang with me. It'll be there. So 0 goes in for T. Anything to the 0 is 1, so it's just 1 plus C equals whatever 800 divided by 25 is, what, 32? So we get C equals 31 if we subtract 1 from both sides. That's our function. We get to utilize that for, I got this now, what is it, 800 over 1 plus 31 e to the negative, 0.04728 t. You got the idea, blah, 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 t. That's the function we can use then to evaluate that last question is, what's the population at a given year, sub in your year, good to go. I want to move on to the next one because this is where the real fun gets to. So I think did that get us through all those? 11, 12. Might want to get to another one, maybe 13. Let's go back to the beginning page, look at what was asked for. 13, so we got this decay function, and it rounds down that decay. When do we get to a certain year? Oh, I cut it off. I'll have to pull that up in another picture in a minute. Before that even, I want to get to 16, so I'm going to fast forward a little bit, add you guys a page, and go to 16. Better yet, 15 and 16. This number 15 is Euler's method, and then what's true about this? Here's the general idea of Euler's method. Let's set up the table again, because I did this for the other block, and I think I'll do it again in another recording, just for another review for you guys. We got x, y, delta x, we have dy dx, we have delta y, and y nu. So these are the things that we put into the table, and y nu is just like the new y that's projected y using the differential equation rather than the actual function itself. Okay, so here's our little table all set up. You start with an initial value, and the way the table goes, we call the x naught and y naught. And delta x is a fixed value. Delta x comes from whatever your interval is, so however wide it is, b minus a, divided up into a certain number of pieces that's decided by the problem. So you want to break it up in how many steps, we call it. So delta x will be determined by that. So if you have an interval of 16 wide and I'm supposed to divide it up into 8 steps, that'd be 2 units delta x per step. So now the next question, the first question is, which one of these apply? And delta x, by the way, is the uniform change in x. So this is always, a dx or a delta x. Another way of saying dx is called delta x, change in x. So that's how we get to x1. We just go up one delta x unit, and then another delta x unit to get to x2. That brings us to the first part of this, part 1. It says, hey, is x2 x naught plus 2 dx's or delta x's? Yeah, as a matter of fact, it is. 2 hops of dx to get to x sub 2. x1, y1 lies exactly on the solution curve. Well, x1, y1, you're wondering maybe where y1 comes from. Well, y1 is what comes from the work that we do in the table. Delta x is fixed, so we have some number. Okay, dy dx is a calculation. I'm going to put this maybe in bold red. The calculation for that is, if you think of, it's actually given, let's do this one, given function. And we'll use it. Somehow they'll give you the differential equation. It's the delta y that I'm actually going to get to as a kind of a cool function. That delta y comes from, if you guys think of delta y over delta x is how you get slope, right? How you get m, change in y over change in x. If you solve for delta y, what we have is delta x times m. And m is our derivative. The slope m comes from our derivative equation. Delta x, well, we've been given that from the beginning. So this getting delta y, change in y, is to take your slope, your dy dx value. And dy dx comes from plugging these x values in your particular row into the derivative dy dx function. You get a number. That number goes in here as m times delta x, and that'll get you delta y. Y new is a result of taking, y old, in this case, whatever your y naught is in this particular case, plus delta y, your change in y. So it's just, your new, y new is a result of taking the old, adding on the new, delta y change. There you go. So each one of those steps, now that's really informal. That's just to give you a sense of how the table plays out. It'll help you answer this question. x1, y1 lies exactly on the solution curve. Well, what the Euler's method does is it takes, and instead of having the actual function, which we don't have, it takes and uses the dy dx, the slope at this point, okay, at that particular point. We go over one delta x unit, right this way, so we get to delta x of some kind, and we plug it into it. We get our change in y as a result of that delta x, and it gives you a point on that tangent line rather than the curve itself. So what we get is this new x1 from going over a delta x unit, and then y1 is the corresponding y with it on the derivative curve, not the original curve. The whole idea of Euler's method is it's not exact. The more iterations, the smaller the steps that you take, the closer this gets to mimicking the curve. But in a concave up curve like this, we're going to be underestimating by quite a bit. But if you break it up into small enough pieces, it'll be pretty darn good. So the way this works out is, yeah, the first one works. The second one, it's not exact, and that's the whole point. It's not exact. It's a great means of an iterative way to get to the exact function. If you make this iteration small enough, you'll get the exact. That's what computers are for. And by the way, that's how your finite function works on your calculator. It uses a form of Euler's method to do antiderivatives, so they can get you the original function. Now, this last one says, hey, is y3 equal to y2 plus this thing dx? Well, y1 goes with x1, y2, x3, y3. Well, the way this always works is y3 is a product of taking y2, that's the y old, plus change in y. That'll give you your y new, and this y new always ends up being your next y in the function. Okay, so if I go over my y2 plus my change in y gives me my y3. Well, this function has y2 plus what? This thing? We'll take a look what that's made of. F of x to y2, do you remember that's, if you look up top, that's your differential equation. F of x, y is our differential equation. So they're saying, is it equal to dy dx times dx? And if you remember, that's how we got delta y. Delta y is equal to dy dx times delta x, or dx if you want to call it that. So really what this is stating y2 plus change in y. And that is a true statement. y3 is going to come from y2 plus a respective delta y. And so that is also a true statement. It's just kind of piecing apart that Euler's method. So in this case, 1 and 3 are true. Answer B. Okay, we're going to get to the last one. Euler's method, let's do the real deal. Now you want to do a little bit of this by hand, and then from there, then you want to quickly stop doing it by hand. You want to get yourself onto a calculator and use the Euler method program. Okay, so you do 16. These are the things they give you. They do give you an initial value. If you kind of read through the lines there, sometimes it's not obvious, but it's saying your initial starting point is 1, 2.5. Your delta x, they actually give it to you, is 0.1. And then dy dx is this lovely formula of, what is it, e to the x. I'm going to forget what it is all of a sudden. Hang on just a second. I can look it up. And we get 4 to the x minus e to the y. Just had to turn my page. I guess I could turn back. All right, there you go. That's your delta x, or dy dx, I'm sorry. We plug in the respective x's into that formula, so whatever we get from 4 times 1 point, in this case 1 minus e to the 2.5, we're going to get that calculation, and that means 4 minus, let's say e to the 2.5. We get this negative 8.1824, so not a particularly nice number. And then that's going to be part of our calculation for delta y, because you remember what that is. That's dy dx, whatever we got there, times delta x, which is a fixed value, 0.1 right now. So I'm going to take this lovely number that I got here, which I already kind of got negative 8.18 blah, blah, blah. I'm going to take it times delta x, so I'll just write that all in there, negative 8.1824, maybe 25 if I round a little bit, and put 0.1 in there. That's how we're going to get delta y. It is a value. So I go to times 0.1, get negative, move the decimal couple a place over. So negative 0.818. Well, y new is always from the old y, so y old, 2.5, plus this change in y that I just got. So I'll take this little dude right here, this calculation, put it right there, and it's about negative 0.8183, something like that. So we'll take that plus 4, or plus 2.5, I'm sorry. We get 1.68-ish, 1.6818, something like that. That's our new y. That's the one that goes in. That's our y. This is x2 and y2 in the next row. x2 comes from going up 1 delta x, so it's 1.1, adding my delta x. And my y new is this 1.6818. Oopsie. 6818. Voila! And then we do it again. Delta x is the same. And then when we do our calculation for dy dx, it's for this new 1, our new x, 1.1, and then minus e to the 1.6818. Cool. And then we do this, repeat this process, take that times 0.1, blob times 0.1, and we take, by the way, this is the blob of this thing, and then take that result, add it to my y old, which is now 1.6818, plus this new y new, and I'll get my next result. Now that's the table by hand. Well, you don't want to do that the whole time. The calculator program that I gave you guys yesterday that I infected you with, the Euler's method disease, that's going to work beautifully. Now the first thing you want to do is go to y equals, and you want to put in that function, which is 4x minus e to the y, and you actually have to use alpha, the alpha key. So alpha and number 1. So alpha 1 will give you a y. You plug it in there with a y. I know it sounds strange. But the way the program works is it calls on that y1 to be your differential equation. You run the program, go down to Euler. If you don't have it, I have some cords on my desk. Just run up there and grab one of those. Plug into a friend who's got it. Hit enter. It says initial x 1, initial y 2.5, final x. You notice it says go from 1 to 2 step size. So I'm going to put in 2 as my final x. 0.1 is my step size. Show the steps. Yes. You're going to build the table based on these steps. And if you hit enter, you should see your first is 1. 2.5. Let me get my highlighter into a different color. And I'll maybe a little green how to do it. So yep, check, got those. Hit enter again. We get 1.1, 1.6818. Awesome, check. Then we do another interval. And this thing fills right in. I get 1.2 and 1.58. It says go to the nearest thousandths, I think, in the instructions. So we can round now to 1.584. And we continue on until you get to 2, comma. And that last number you get, that's the one we're looking for. We're trying to get to that result. If you need help with that, would you contact me? Let me know what I can do to get you on board. That's it. There's your 20 minutes of my information. Some of it we've already seen. Anything else you need, you want to contact me. I'm actually going to do a video, a very special video, of the one that gave the other class a little bit of trouble. Let's see if we can get back to it at the very beginning. Oh, here we go. Where are you? No, it's not 13. It must be 14. Is that the one? Let me do that. I'm going to add a page here. Let's pull up number 14. I don't know if you guys can see what I'm doing, but I'm going to pull up 14 for you. And it looks like, yeah, this little guy. Done. Here, there's 14. And that 14, this one, how does it get to 0? This is a crazy, mind-blowing problem, and I'm sorry, fourth block, I'm not there to help blow your minds because you'll really dig it. You'll think it's impossible. Some people are still arguing against me. But please look to your computers, check out what I do for number 14. I'll make that a separate video. Hasta la vista. I'm going to be out tomorrow. Graham's really still sick. He's in the hospital, and I'm going to swap shifts so that my wife can go to work a little bit this week. And so I'll be gone tomorrow. You'll take a test. You'll be very prepared. Take a look at this review. You'll find ways to retake it with me, but do your best, as I know you will. And send me emails. See you guys later.